Okay, welcome to lesson 2 for quadrilaterals, and the focus of the lesson 5.2 is ways to prove quadrilaterals are parallelograms. And so just a quick reminder, by definition, if both pairs of opposite sides of a quadrilateral or four-sided figure are parallel, then by definition that quadrilateral is a parallelogram. And so what we're going to do now is focus on essentially what are the converses of theorems 5.1, 2, and 3, which relate to the properties of parallelograms. And these converses are ways in which we can prove that a quadrilateral is in fact a parallelogram. Okay, and so we're going to begin with theorem 5.4, which states that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. And so this is the converse of theorem 5.1. Theorem 5.1 said if a quadrilateral is a parallelogram, then both pairs of opposite sides are congruent. This is the converse. If both pairs of opposite sides are congruent, then it is a parallelogram. And so, as usual, what we'll do before we use the theorem in other proofs is do a formal proof of theorem 5.4. And so what we are given is that BC is congruent to AD, and similarly we are given that AB is congruent to CD. We have been asked to prove that ABCD is a parallelogram. As usual, we must avoid a logic flaw. We cannot use what we've been asked to prove in order to prove it's true, and so we cannot make the statement that ABCD is a parallelogram and therefore that proves it is. What we're going to need to do is prove that having both pairs of opposite sides congruent will in turn allow us to show that both pairs of opposite sides are parallel, and this in turn by definition shows that the figure is a parallelogram. Okay, and so as we've been doing for the previous unit and again this one, what we're going to be using is congruency of triangles. Based on the markings you see, we have constructed segment AC, which joins non-consecutive vertices, and segment AC is a diagonal of the quadrilateral, and it is a reflexive side between triangles ABC and triangle CDA, and this shows very clearly where we'll get our congruency of triangles. And what we're going to do with the congruency of triangles is show that angle 1 and angle 2 are congruent to each other, and angle 3 and angle 4, and we are going to do this because these are alternate interior angles, and if we can show that they're congruent, then congruent alternate interior angles imply parallel lines. Okay, so we've verbally laid out the proof, and now we'll go ahead and do a formal write-up. And so we begin with BC congruent to AD and AB congruent to CD, and that information was given. We have segment AC congruent to segment AC, and that is because of the reflexive property. Okay, alright, and that allows us to say that triangle ABC, so we're going from A to B to C, and so I must go CDA, triangle C to D to A. Those are congruent by the SSS postulate, and we are now in a position to say that angle 1 congruent to angle 2, angle 3 congruent to angle 4, and that is because of CPC-TC, corresponding parts of congruent triangles are congruent, and in turn we are able to conclude that AB is parallel to DC, and BC, segment BC, is parallel to segment AD, and that is because congruent alternate interior angles imply parallel lines. And our final statement is that ABCD is a parallelogram, and that is by virtue of the definition of a parallelogram. Okay, and so now we have formally proved the theorem 5.4, the converse of theorem 5.1. Okay, and so listed out theorem 5.5, 6, and 7 are three additional ways of proving that that a figure is a parallelogram, and we can prove that by proving one pair of opposite sides both congruent and parallel. So that's one of the ways. That is not a converse of one of the previous theorems from the previous section, but a combination of a couple of pieces. Theorem 5.6 and 5.7 are both converses. Okay, and so now what we're going to do is apply theorem 5.7. Theorem 5.7 is the converse of 5.4, which we formally proved in the previous lesson. And that this theorem states that if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Okay, and so here's an application of that theorem. We've been asked in this case to find the values of x and y that will make the given figure, the given quadrilateral, a parallelogram. Okay, and so what we can ascertain from this is that in order for this figure to be a parallelogram, the diagonals would bisect each other, and so the values of x which would cause this to be so would be obtained if we take the x and equate it to 3x minus 40, and that would mean that the two segments were equal to each other. If we go ahead and solve for x at this point, relatively straightforward equation, and we have the value x is equal to 20. Same approach for the other diagonal. This time, however, we have a quadratic equation. Y squared is equal to y plus 30. This can be easily solved using factoring, and so I'm going to begin by rearranging the equation, equating to 0, and then we'll factor out our trinomial. Factors of 30, which are going to give you 1, are 6 and 5, and we're going to have minus 6 plus 5. That allows us to conclude that y is equal to minus 5 or y is equal to 6, and naturally the answer y is equal to minus 5 is an unacceptable solution, because we cannot have a negative, I beg your pardon, sorry, in this instance, if we look back at the original, in fact, that solution is acceptable. If we substitute back in, it will nonetheless produce acceptable answers. My apologies for that. Okay, and so at this point, what I'd like you to do is move on. There are 4 practice problems which tests your understanding of the theorems that we discussed on the first page of the note. What I'd like you to do is to try each of these 4 and then watch the second part of the video recording, which will give answers to this, and you'll be able to check your own understanding of the 4 or 5 different ways of proving that quadrilaterals are parallelograms.